Well, thank you for staying all the way to the end of your first day. I can guarantee that tomorrow it will be even harder. So, what I'm going to present today is some work that we've done in trying to understand changes in the mean state of the ocean between today and the last glacial maximum and its implication for the carbon cycle. This is work done with a very large number of collaborators that I'm not listing here because not every collaborator contributed to all the ideas here, and I didn't want to force them to agree with everything I have to say, but they'll all be listed at the end, and you can see who contributed to what. The motivation for this kind of work is easy to summarize. We're just looking at one of these iconic pictures from the Vostok ice cores of drops in temperature for every glacial period associated with a strong drop in PCO2, in atmospheric carbon dioxide concentrations. What it is believed, and you heard it in a number of talks before mine today, that this association is linked to changes in the state of the ocean because it's the only reservoir that could have taken up this excess carbon. So we want to understand a bit more mechanistically how that connection might have come about. So I start by reviewing some work that we published earlier this year in PNAS with a large number of co-authors, and you should go to that paper if you want to understand in detail what I'm going to say. Here I'm trying to summarize the basic idea to ramp up and explain the implication for the carbon cycle. So we start from some basic understanding of the present-day ocean stratification for the deep ocean. I'm concentrating on the deep ocean because that's where most of the carbon is stored, both in the present day and supposedly in the last glacial maximum. This is a section of zonally average density. This is depth, latitude from the southern hemisphere to the northern hemisphere from present-day climatology. This black line demarcates the southern ocean, so these are the latitude of the southern ocean where you have this strong Antarctic circumpolar current, and this instead is the region spanned by the Pacific and the Atlantic basins. I want you to notice that density surfaces are nearly flat in the ocean basins, but they become extremely steep in the southern ocean. We know what sets that slope dynamically. It's a combination of wind and turbulence or eddy activity. And we also know that that slope is not going to change much between present day and glacial periods because you might expect winds to change up to 5 to 10%, but they're going to be small changes. So we can take that slope as given both the present day climate and the last glacial maximum. Now what is nice about this picture is that then if I know the density distribution at the surface, if I know the value of a particular density surface, then I know what slope it's going to take in plunging down in the southern ocean. Then once it reaches the northern edge of the southern ocean, it's just flat. So I can reconstruct the full stratification of the ocean just knowing something about the surface properties. So it's a helpful constraint when we want to interpret changes at the last glacial maximum. We can go a bit beyond that and try to also add some information in the same flavor about the circulation itself, not just the stratification. So now I'm going to draw a box. This is again the same section as before, but we are focusing on the southern ocean. And I'm drawing a box which represents the summer sea ice, so it's permanent sea ice. And now the dashed line is the isopycnon, or the density surface that outcrops at the sea ice line. Now, if we want to know something, so second thing that we know is that once I've drawn this ice line, it's the extent of the ice, that it helps me to say something about the surface air sea fluxes. We know that under sea ice, buoyancy fluxes tend to be negative, mostly because of brine rejection, while north of the permanent ice line, buoyancy fluxes will tend to be positive because of summertime warming, ice melting, and freshwater fluxes. So the ice line is a very good demarcator of region of buoyancy loss, regions of buoyancy gain. We've done work with reanalysis to confirm that that is actually true in the present-day configuration, in the present-day ocean. Now, with these two pieces of information, we can reconstruct the zonally average overturning circulation because we know in the ocean interior, flows are mostly along density surfaces. So this water, the waters that move along the density surface but slightly below it, now they are upwelling under a region of buoyancy loss. Therefore, they are made denser by the interaction with the surface, and they move southward and they sink. Waters that instead flow along that density surface but slightly above it are going to move up along the density surface. When they come to the surface and they are exposed to their sea fluxes, they are made lighter, and therefore they move in the other direction. So we see that just by knowledge of the sea ice line, we can reconstruct this two-cell circulation that we all know is characterizing the present-day overturning circulation in the Southern Ocean. Now we have to close the circulation. That was just the Southern Ocean perspective, and this is a cartoon where we can try again. This is the Southern Ocean. These are the two cells, but now we are going to color code the branches of the circulation according to the water mass that they are associated with, and this cartoon is inspired by work done by Lynn Talley recently. So if we start now from the northern hemisphere, this is the North Atlantic, and this is waters that sink in the North Atlantic through convection. These waters sink at depth, and they move all the way to the Southern Ocean. Turns out that the core of these waters is of order of 28.1 kilogram per meter cube in neutral density in the present-day ocean. That's denser than the density surface that outcrop at the permanent sea ice line today. Therefore, this water, when they upwell, they are still below this density surface. They all get converted back into Antarctic bottom water. The Antarctic bottom waters then sink around Antarctica and flood the Atlantic and Pacific. This is dead. I don't know, maybe. Yeah, it doesn't get there. Okay, this works. So then these waters flood in the Atlantic and Pacific basins. We know that the way these waters come back out to the surface, they are exposed to turbulent mixing in the abyssal ocean that mixes them with lighter waters above. Turbulent mixing is particularly efficient just below 2,000 kilo. Oops, now I have the problem. No, touching it too much. Turbulent mixing is strong in the ocean only below 2,000 meters because turbulent mixing is associated with breaking waves. The waves are generated close to topography. Most of the topographic features that are indicated with this gray line, meaning abyssal hills, rises, are most prominent below 2,000 meters in the present-day ocean, and therefore you expect this water to be mixed all the way up to close to 2,000 meters. That is just barely enough for this water to cross this density surface that outcrop at the sea ice line. So if this water comes slightly above, by the time they come back into the Southern Ocean, they are exposed to a positive buoyancy flux, and they return back towards the North Atlantic. So what is important in this picture is that you have dense water sinking in the North Atlantic, and you see that there is this loop that connects all the circulation until you come back to the North Atlantic. It's like a figure-8 loop, if you want to call it that way, but there aren't really two separate cells. It's just one continuous cell that spans all the oceans, and I think here I went way too far. So what do I think changed fundamentally at the last glacial maximum? Well, one thing that we probably know about the last glacial maximum is the permanent sea ice extent has expanded. There is disagreement by how much, but somewhere between 5 and 10 degree latitude in summer conditions, taking a conservative value of 5 degrees. Well, if this sea ice line has expanded, now we can see what happens to the density surface that outcrop at the sea ice line. Now, this density surface outcrops here, the sea ice line has expanded. As I said, the slope doesn't change all that much, no matter what climate you look at. That is very well supported by all kinds of numerical simulation of full 3D ocean models. So this density surface now hit the northern edge of the Southern Ocean at a shallower depth than it did before. It turns out that it hits it 500 meters. It's at 500 meters less, or it's 500 meters shallower than it is in the present-day ocean. Now, this has important implication for what the circulation will look like at the last glacial maximum, because I moved this density surface that was sitting in a region where it was experiencing strong mixing in the present-day ocean to a position where it's not experiencing mixing anymore. Mixing, as I insisted, is really associated with the bottom topography. The bottom topography didn't change much on the kind of time scale we are talking about. So now this water of the circulation at the last glacial maximum, now if we start from Antarctica, it sinks all the way to the ocean bottom, it floods the Atlantic, the Pacific, and the Indian Ocean. Now it gets mixed up to the top of these major topographic features and returns back to the Southern Ocean. Is still denser than this density surface that outcrop at the ice line, so this water folds on itself, and now you really have a closed cell. And now you only have an upper cell that is confined to the surface that doesn't interact anymore. Now you really have changed the topology of your circulation. Just to provide some context of why this kind of rearrangement of the circulation is consistent with what we know about paleo observations, at least I'm showing what, again, it's an iconic picture of delta C13 as a tracer between, in the Western Atlantic, two sections one for the present-day ocean and one for the last glacial maximum. We heard now that there are better or more complete maps that we could also use to look at this. And what I'm showing is just that you have this tongue of North Atlantic deep water, very rich in delta C13, which is my gray line here, and it's intruding over this more depleted delta C13 waters, which is your Antarctic bottom water down here, my blue line. As you move to the last glacial maximum, you see that indeed there is an expansion of waters of southern origin, and this, in our interpretation, would be associated with this expansion of the bottom cell, the closon itself. It's important to notice that the expansion is not just the expansion of this density surface of moving upward, it's really the overall circulation. All of a sudden, it's just connected to the Southern Ocean. We've done more work, and Andrea Berkey, one of the co-authors on this work, is going to present a poster, or probably the poster is ongoing, I don't know at this point when things happen, where we also use delta C14 to provide more constraint and more support for this rearrangement of the circulation I've shown you, so I encourage everybody to go and look at that poster. But now, as promised, I want to explore the implication of this rearrangement in the circulation for the carbon budget of the glacial ocean. And I think that there are two main aspects of the story that I want to emphasize, two main aspects of this rearrangement of circulation that are potentially very important for changing the carbon budget of the glacial ocean. The first one, as you already all noticed, is that there is an expansion of Antarctic bottom water in this story, which is strongly supported by observation. But the second part is also that, if you remember, I insisted that this branch of the circulation that moves southward is constrained to just exist under the permanent sea ice line. So in the present-day ocean, waters spend very little time under the sea ice, and therefore they spend little time at the surface. In the glacial ocean, instead, they spend a much longer time because the sea ice line has expanded. That might have impact on productivity in the Southern Ocean. We're going to quickly look at both effects. So the first one is what Luke Skinner called the standing volume effect. Just the fact that you expanded this water would have increased the amount of carbon stored in the ocean, therefore have dropped PCO2 concentration. You can do the calculation by how much the PCO2 would have dropped in a simple way by just saying, well, we know in the present-day ocean waters below 2,000 meters are 35% of northern source and 65% of southern source. These are typical estimates from state estimates in the present-day ocean. We know how much carbon there is in the abyssal, say, in the southern source water versus the northern source water. As I move in the glacial maximum, I insist that pretty much all the waters below 2,000 meters become a southern source water. So as a perturbation calculation, I can indeed find out how much more carbon was stored in the abyssal ocean, because I convert the carbon-rich waters for northern source carbon-poor water, and that is converted to a drop in PCO2 of order 30 ppm. That number is very consistent with a similar calculation done by Luke Skinner that used a more complete biogeochemical model and just used the fact that the expansion was evident in the data and just computed the standing volume effect by itself. Here we are providing a rationale of why that is happening, but the calculation is essentially the same. We can also look at the change in the biological carbon budget, or the increase in productivity. As I said, the water now is spending more time at the surface. We know that in present-day ocean, these water do not utilize all their nutrients, mostly because they spend too little time at the surface. Now the waters spend more time at the surface. It turns out that they spend twice as much time at the surface because of the expansion of sea ice. Actually, you can find that the change in biological carbon is just proportional to the change in residency time at the surface, which in itself is proportional just to the expansion of the sea ice line. These things all scale linearly with each other, so the nutrient utilization efficiency goes up in the southern ocean because this cell spends more time at the surface, and the implied carbon drop that you can estimate is of order of 50 ppm. So if you sum these two numbers, 50 plus 30, you get something of the order of 80 ppm. So I think that what this framework is providing is, these are ideas that, for example, have been talked about by Dennis Sigman for a long time. What this is providing is a framework to understand how all these different pieces might fit together and explain how you enter in a glacial state and how the carbon budget responds to it. First of all, here is the list of all the people that contribute to the various parts of the work. I think Jess Atkins, the only one who is guilty, as me, of contributing to all aspects. All other people, they're just to be blamed for only part of it. As I said, just very quickly, the big change in circulation between the present day and the last glacial maximum is that in the present day you have this completely connected overturning circulation, and the last glacial maximum, the circulation splits into separate cells. The lower cell becomes an effective carbon storage system because the overall productivity of the Southern Ocean increases. And I'll stop here and maybe take questions.
Thank you very much. That was great. Since you're the last one, I think there is time for some questions, if there are any.
Well, here I'm only talking about mean states. I'm not talking about transition, so I'm not going to address stability per se.
But you have geo events, you have orbital forcing, the Southern Ocean, you have all kinds of things that will change the sea ice extent, the mean.
Oh, the mean sea ice extent. So you want to know about changes in the circulation or changes in the carbon budget? I mean, yes. I mean, there can be other states. Here I'm really talking only about the glacial maximum, the present state. There are a lot of states in between that we could start discussing. And there are solutions for each one of them, whether there is really a steady solution or in some of them it's a transient, I don't know. It would be worth exploring.
But we know that CO2 is relatively stable during these times. It seems unlikely that sea ice extent.
Here we are talking about summer sea ice. And summer sea ice, I mean, you have some wiggle room, but, you know, there are limits about how much you can change. You're talking about 1 degree, 2 degrees, that's not going to do much. It has to be a pretty substantial change before you have this rearrangement of circulation. And you really have a transition between two topologically different states. It's only when you transition across them things really change. It's not just small changes that will take you from one circulation to the other.
Ralph, is there a conflict between the relative isolation of the lower circulation during the glacial and the many observations that it appears to be driven by a northern template
So
in terms of glacial to interglacial changes?
So, thank you very much for the question. I think no, there is no inconsistency. This is a reconstruction, call it a diagnostic reconstruction of the circulation. What I'm insisting, and we know it's true for the present-day ocean, and I strongly believe it's going to be true for the southern, for the last glacial maximum, it's in a constrained sense. If I know something about the structure of the Southern Ocean, I can reconstruct the rest of the circulation. I never said that what drives those changes in the Southern Ocean. For example, you could very easily, I mean, if we want to start in storytelling, go into storytelling, I could insist that why did the sea ice expand in the first place? Well, it was water sinking in the North Atlantic that, for whatever reason, was colder at some point, and that allowed the sea ice to expand. Once the sea ice expands sufficiently, then I create this closed loop. So what controls is a very different story, and it could well be it's a North Atlantic control, and it probably is.
Eric?
So your mechanism calls on there being a lot of export production underneath the sea ice. Do you have observational evidence to suggest that would happen?
So, okay, another great question. Did people hear the question? The question was, I'm talking about an increasing productivity under sea ice. So do we know that productivity can continue under sea ice? So the reason why I took that view for what I was going to present here, first of all, I didn't have much time to take more than one view. The reason why I took that view, what I mean by permanent sea ice, I mean this is sea ice that is there 70% of the time in summer. So there is quite a bit of opening. So the evidence is that yes, there is occasional polynias and opening up. You could still have a pretty productive ocean. It doesn't necessarily suppress it. But you could take the opposite view and say, what about if that ice was really there 100% of the time and completely sealed the Southern Ocean? Well, in that case, the productivity, if anything, goes down, but now you're really sealing those water, you're reducing the air-sea exchange. In that case, it's the air-sea exchange, and you go back to ideas that have also been proposed. It's just a lid on top of the ocean, and that would also drop the CO2 levels. Probably less than the numbers I put for the carbon pump change. We estimated something of order 30 ppm, but again, you're in a similar state. You just isolated those waters. That's another potential solution within this framework.